Algorithms like logistic regression try to draw a perfect line between different categories. But what if we approach the problem in reverse? Instead of finding a boundary, we work backward from the visible evidence we have to calculate the invisible category that created it. This map of classification algorithms highlights our current focus. Algorithm number 28, naive Bayes. The architecture powering modern spam filters isn't a recent invention. It relies entirely on an unpublished theory written by an 18th century minister named Reverend Thomas Bayes. Bayes devised a mathematical framework for backward reasoning. He realized that if you know how often an effect occurs, you can mathematically deduce the probability of the hidden cause behind it. In 2002, programmer Paul Graham applied this centuries-old theorem to the early internet. He wrote an essay titled A Plan for Spam, detailing how to use Bayes' math to teach machines to identify junk mail automatically. Processing text data is mathematically exhausting. An inbox contains thousands of unique words, and trying to compute the exact relationships between all of them demands massive computational power. To filter billions of messages across the internet without crashing servers, computer science required a highly efficient approach. The solution must process data instantly, require very few training examples, and cost almost nothing to update. The core engine of this algorithm operates on one strict rule. To find the most likely category, you take the baseline probability of that category, multiply it by the likelihood of the evidence you observe, and simply pick the highest score. Looking at this grid breaking down occurrences of astigmatism and beards, we can see exactly how the formula is derived. By dividing the joint occurrences by the total probability of the evidence, a difficult probability question flips into an easy calculation based entirely on visible attributes. The equation isolates the exact variable we want to predict. It proves a system can calculate the exact likelihood of a hidden trait by counting how often related features appear together in the real world. But scaling this exact theorem creates a massive bottleneck. If you try to calculate the true combined probability of thousands of interdependent words in a real dataset, the math becomes too complex for a standard processor to handle. This is where the algorithm gets the name naive. Engineers made a deliberate decision to break the rules of statistics. They built a system that simply pretends every single feature in a dataset is completely independent of all the others. That intentional lie solves the computing problem. By ignoring how words interact with each other, the algorithm collapses an impossible tangled matrix of probabilities into a straight, lightning-fast line of simple multiplication. Let's run a live test. Imagine an incoming email arrives containing exactly 3 words: win, money, and now. The system sets up a race. On one track, it calculates the probability for spam. On the other, the probability for ham, or normal mail. It takes the baseline chance of each category, then multiplies it by the independent decimal probabilities of seeing win, then money, and finally now. The calculation finishes, and the algorithm applies an argmax function, a mathematical command to select the highest resulting value. The spam track produces the larger number, so the email is immediately flagged as junk. But before that race even starts, the system needs the decimal values for each specific word. This table shows exactly how those estimates are generated. Training this algorithm requires no complex logic. The computer reads through a labeled dataset and literally just counts the frequency of each word inside each category. You will notice a +1 added to the count. This is a fixed called Laplace smoothing. If a completely new word appears that the system has never seen before, its probability would be 0. Multiplying by 0 destroys the entire calculation, so adding 1 ensures the math keeps running. The text also references log probabilities. Because multiplying dozens of microscopic fractions together causes computer processors to round down to 0, the algorithm adds logarithms together instead, keeping the final numbers mathematically stable. This scatterplot demonstrates what happens when the algorithm shifts away from discrete text and looks at continuous numerical data, plotting feature coordinates on a graph. This plate notation diagram illustrates how the system adapts. Instead of basic counting, the algorithm uses Gaussian bell curves, mapping continuous numbers to a probability distribution using the exact same underlying logic. Combining Laplace smoothing, log probabilities, and Gaussian distributions takes an 18th century theoretical concept and hardens it into a resilient industrial-grade engine. The entire process boils down to 3 mechanical steps: count the occurrences in the training data, multiply their probabilities together, and pick the largest resulting score. It doesn't trace complicated decision boundaries through space, and it doesn't require millions of artificial neurons to find an answer. Because the math is so basic, the algorithm operates almost instantaneously. It thrives on massive, high-dimensional datasets that would force heavier, more sophisticated models to stall. By intentionally ignoring the tangled relationships between variables, naive Bayes proves that sometimes the most effective way to solve an infinitely complex problem is to simply pretend the complexity doesn't exist. Now that the theory is clear, it's time to see it in practice. Next, we will open up a Python notebook and see exactly how few lines of code it takes to build this probabilistic engine from scratch.
But in a modern machine learning environment, thousands of raw data points can snap into a mathematical structure almost instantly. To see exactly how this works in production, we are looking at the exact Python source code from the 50 algorithms repository. The pipeline starts by dividing the data. We separate our input feature matrix, X, from the target labels we want to predict, Y. We apply the train test split function, allocating 75% to training, locking the remaining 25% away for testing. Quarantining a quarter of the dataset ensures that our final accuracy score measures the model's ability to classify unseen data, rather than just testing if it successfully memorized the training rows. In this specific dataset, predicting automotive fuel efficiency based on features like horsepower and engine displacement, these are continuous, non-discrete decimal numbers. This strict separation of continuous inputs and hidden test data provides the structural boundaries required for probabilistic modeling. This creates an immediate mathematical problem. Naive Bayes was originally designed to count discrete events, like the number of times the word cash appears in a spam email. You cannot count the frequency of an infinite decimal like horsepower. To process continuous numbers, we must abandon the standard event counting logic and apply a specific mathematical variation of the algorithm. This diagram maps 3 naive Bayes variants. The Gaussian variant solves continuous data by assuming features follow a bell curve distribution, defined by mean and variance. This pivots from multinomial naive Bayes, which relies exclusively on token frequencies and fails on decimal ranges. In practice, the scikit-learn library handles this complex distinction entirely behind the scenes. The engineer simply imports the Gaussian NB object class. Choosing the right algorithm is a matter of strictly aligning the statistical assumptions of the math with the physical shape of your input data. We instantiate the Gaussian object and then execute the .fit command on our training data. That single line of code comprises the entire training phase. There are no iterative optimization loops here. The algorithm never calculates a gradient descent. Look at the likelihood table in this graphic. Under the hood, the .fit command makes exactly one pass through the data, calculating the prior probabilities, the means, and the variances in a single definitive sweep. This single pass calculation dictates the training time complexity. It executes in O of n times d times c. Because the math only requires reading each of the n samples once to update the statistical averages across d features and c classes, the required compute time scales perfectly linearly. The .fit method does not learn through trial and error. It operates as a highly optimized statistical calculator, guaranteeing its instantaneous execution. With the statistics locked in, we move to deployment, executing the .predict command on our quarantine test data. For every new row of unseen data, the model computes a distinct probability score for every possible class. It executes a strict mathematical argmax operation, multiplying the class prior by the product of the feature likelihoods and selecting the highest resulting value as the final prediction. Notice the callout box in the bottom right of this slide. Because the model only needs to evaluate the D features across the C classes for a given input, the time complexity of prediction drops to O of D times C. It is completely decoupled from the size of the original training data. We then run metrics.accuracy score to validate these generated predictions against the hidden labels we held back at the start.
By turning complex probability into a vectorized lookup and sum operation, naive Bayes achieves extreme prediction speeds, making it ideal for high-volume, real-time deployment. On this dataset, the code returns an accuracy score of exactly 92%. That is a highly competitive result for an algorithm with 0 tuning parameters. But a single percentage point masks the specific contours of the model's errors. To map out where it actually fails, we generate a confusion matrix. The matrix categorizes every prediction, cleanly separating the false positives, where the model confidently hallucinated a result, from the false negatives it missed entirely. These specific errors are the direct cost of the algorithm's foundational mathematical assumption. The green box outlines its absolute strengths: 0 compute overhead, scaling to thousands of features, and acting as an unmatched baseline. But the red box exposes its ceiling. The algorithm assumes every feature operates entirely independently. In reality, variables almost always influence each other. 3 lines of code yield a closed-form model that trains instantly. You aren't limited to text processing either. You can adapt the algorithm to handle entirely different kinds of data just by swapping out its underlying probability model. This diagram outlines 3 variants. The multinomial model is your standard for frequency counts, like document sorting. For strict binary outcomes, present or absent, swap to the Bernoulli variant. For continuous data, like heights, use Gaussian naive Bayes, forcing a bell curve distribution. Whether you feed it yes or no flags, frequency tallies, or continuous decimals, the core engine scales to thousands of features while requiring very little training data to get off the ground. The consequences of this trade-off become obvious when the independence assumption inevitably breaks down. In the real world, words like new and York heavily influence each other. When the algorithm forces them apart, the logic begins to fray. Because it ignores these natural correlations, the final output probabilities are severely poorly calibrated. You should never trust the exact confidence percentages a naive Bayes model spits out. But here is the catch. Even when the percentage scores are wildly inflated, the actual ranking remains correct. The tallest bar is still the tallest bar, meaning the model usually picks the right winner, even if its internal math is skewed. You do have to be careful with the Gaussian variant. If your continuous data is heavily skewed and doesn't naturally fit a bell curve, that forced assumption will completely ruin your estimates. You also have to apply a safety net called Laplace smoothing. If your features are strongly correlated, you'll need models like logistic regression or decision trees, which can actually account for how features interact. These models provide the calibrated probabilities that naive Bayes sacrifices to keep its counting logic so simple. Looking at our map of 50 algorithms, naive Bayes anchors the classification category. It requires mandatory smoothing, and its percentage scores are a fiction, but its raw computational speed and low overhead make it a practical day-one baseline for classification tasks. You can explore the exact Python implementations of these probability models in Imran Ahmad's book, 50 Algorithms Every Programmer Should Know. You can find the full series at neuralsca. Next time, we'll step away from probability scoring entirely and look at how to classify data by finding its closest neighbors.